Variation. We'll look at a couple different types of variation. The first type we'll look at is called direct variation. Direct variation. We'd say things like y varies directly as x. Or you can also say y is directly proportional to x. When we look at this, what it means that y is equal to k, some constant k, times x. Nope. And k is what we call the constant of variation, or the proportionality constant. So one thing that we'll see with k is that it is not a 0, and it's some real number. So if we look at an example, what we can say is that the cost of a smoothie varies or is directly proportional to its size. And then I'm going to give you some other information. So if a 12-ounce smoothie costs $3.60, what I want to know is how much will a 16-ounce smoothie cost? So, in order to do this, we're going to set up a variation equation. And whenever I set up the variation equation, I like to define my variables. So we'll say C is equal to the cost of a smoothie. S can represent the size of the smoothie. And then K can be our constant of proportionality, or variation. So if the cost of a smoothie is directly proportional to, the cost is like the y, it's equal to K times S. We actually have enough information here that we are going to find the value of K and then use it to make a prediction. So if you think about what we know the cost of a 12-ounce smoothie, so the cost is $3.60. And it's equal to the constant of variation times its size, which in this case is 12. So if we wanted to isolate K, we would divide each side by 12. And we'd get that K is equal to 0.30. That means we can write our more specific variation problem. The cost is equal to 0.30 S. And if we wanted to find out how much a 16-ounce costs, then we plug in 16 ounces. So a 16-ounce smoothie would cost 0.30 times $16, or in this case, $4.80. One thing that you will see with variation, it'll tell you that it's directly proportional to, or then in the next example we're going to look at inverse variation. So it would tell you perhaps inverse variation. There's no guess as to what type of variation it is because it's pretty much in the wording. Alright, let's look at inverse variation. When we look at inverse variation, you will see things like y varies inversely as x. Or you may even see that y is inversely proportional to x. Y is inversely proportional to x. And when we look at this, this means that y is equal to k, some constant of variation, times 1 over x in this case. Another way that you could see this, you would also be able to say that y is equal to k, our constant of variation, over x. So we're going to look at an example here as well. And the example is as follows. The time required to rake the grounds at a manor varies inversely with the number of rakers. If 4 rakers can complete the job in 12 hours, then I want to know how long would it take if there were 6 rakers. So if we start this, we are going to define some variables. So let's let maybe capital T represent time. And this is in hours. Maybe we let R be the number of rakers. Number of rakers. And then K is our proportionality constant. So to start this problem, we need to set up our variation problem. Since it is varying inversely, and by it I mean the time, we'd have T is equal to K over R. To find the value of K, we're going to use that we have 4 rakers and it takes them 12 hours. So we'd have 12 is equal to K over 4. To get K alone, we'd clear our fraction, so we'd have to multiply each side by 4. And we'd get 48 is equal to K. So in this case, the specific variation equation is T is equal to 48 over R. And we're not done quite yet because we want to answer the question, how long it would take if there were 6 rakers. So we can plug in the value of R that we know. We would say T is equal to 48 over 6, which we know is 8. So it should take them 8 hours to rake the manor. Now that you've seen both direct and inverse variation, we'll talk about joint variation. So when we talk about joint variation, what we will see is you'll see things like y varies jointly as x and z. That's supposed to be a z. Or you'll see that y is jointly proportional to x and z. Okay, so again, it's in the name, so you'll see jointly, and that's your indicator that we've got something along the lines of y is equal to our constant of variation times x times z. So varying jointly means we're multiplying those two things together. So our example here is the cost of a fence that is 200 feet long and 5 feet high is $3,000. If the cost varies jointly with the length and the height, length and the height. The cost varies jointly with the length and the height. Then what is the cost of a 250 feet long fence by a 6 feet tall? So just like before, we are going to start by writing our variation equation. And before we do that, let's define our variables. This is something that I think is really important to do, and I would like for you to do it. So we have for the length of the fence, and then h for the height of the fence, so if we set this up, the cost of the fence varies jointly with the length and the height. That means the cost is equal to some constant of variation, k, or a proportionality constant, times the length times the height. Okay, we aren't always going to have a specific equation to solve, but because we want to essentially make a prediction, then let's use the things that we know. So we said if the fence was 200 feet long and 5 feet high, the cost was $3,000. So 3,000 is equal to k times 200 times 5, or 3,000 is equal to 1,000k. So we would divide each side by 1,000, and we'd get 3 is equal to k. That means our specific equation is the cost is equal to 3LH. Okay, if we want to figure out the cost of a fence that's 250 feet long by 6 feet high, then we're going to look at C, which is equal to 3 times 250 times 6. And if you go ahead and compute that, we end up with I think it's $4,500. Let me just verify that one more time. 3 times 250 times 6. That is correct, $4,500. So it would cost them $4,500 to build a fence 200 feet long by 6 feet high. Our last type of variation is called combined variation. So here we might have both inverse and direct variation happening at once. So we'll look at 2 quick examples, and then tomorrow or next time in class we'll look at a specific example where we have to solve. So the example that we will start with is y varies directly as x, and inversely as z squared. As z squared. Y varies directly as x and inversely as z squared. So in this case, we're going to think of k as our variation constant, or our constant of proportionality. So y is equal to k, and if it's varying directly as x, that means we're going to multiply it by x, and inversely as z squared. So that's like multiplying by 1 over z squared, which if you think of these as being fractions as over 1, remember when we multiply straight across. So we would have kx over z squared. That is what y is equal to. We can also look at another example. So we can say m maybe it's not always y, but m varies directly as w, and the cube of z. So hopefully when you think of the cube of z, that's like z to the third power, or z cubed. So if m varies directly as w and the cube of z, this means that m is equal to our constant k times w, because it's directly, and the cube of z, so that's times z cubed as well. Again, we will tie together an example where we look at combined variation, and then we will complete an example in class that we can use where we solve for k and we can make predictions.